Good afternoon, everyone, and welcome to the EOL seminar series. It is my pleasure to welcome Ian Cornejo, who is visiting us from the University of Wisconsin-Madison this week. So please congratulate Ian, because this past spring he completed his master's degree at the University of Wisconsin and is now a PhD student working with Angela Rowe. Is that correct? Working with Angela Rowe at the University of Wisconsin. So Angela is his advisor. And the Atmospheric and Oceanic Sciences Department. Ian's research interests focus on the microscale to mesoscale processes and dynamics that contribute to extreme rainfall, specifically in the context of mountainous terrain. So it is not surprising that his current research uses data collected during the 2022 PRECIP campaign. PRECIP stands for the Precipitation of Rainfall Extremes Campaign in the Pacific. In particular, Ian is using rainfall measurements inferred from the NCAR's S-Pol radar. And he will talk more about his research goals in his seminar today, which is titled Extreme Rainfall in Taiwan, Observations from NCAR's S-Pol radar during PRECIP TAHOPE 2022. For those virtually participating, welcome, and please ask your questions in the Slido window located at the bottom of your presentation screen, and then we're gonna have a Q&A session at the end of Ian's presentation. So Ian, welcome back to EOL, and the stage is yours.
We good on volume? Great. Thank you for that introduction. Before I get going, I want to also quickly acknowledge my co-authors, Angela, Ricky, Mike, and John over at EOL. My title is again Extreme Rainfall in Taiwan, and I think first we should have a quick philosophy mention of what exactly is extreme precipitation. That term gets thrown around quite a bit, but we often find that extreme is actually quite contextual. One example that might be near and dear to many of your hearts is the Great Colorado Flood of 2013, whereby 450 millimeters of rainfall produced widespread flooding over much of Colorado. Contrasting this, we can look at Typhoon Morakot over Taiwan in 2009. By Taiwanese standards, this is also an extreme event, but the rainfall that was required to produce it was over 2,500 millimeters of rainfall, or about 100 inches of rainfall. Those are two drastically different amounts of rainfall, but they are both extreme in their respective locations. To be able to compare these two events is quite difficult. We can look at some commonalities, such as the terrain in both regions, Colorado and Taiwan both being mountainous regions, but if you try to examine further than that, it becomes quite difficult. And this is really where the PRECIP field campaign comes in, whereby we're adopting this intensity and duration framework where rainfall can really be broken down into rainfall intensity and rainfall duration. And within those two different variables, you can form a spectrum of rainfall. And we find that rainfall intensity is tethered and linked to convection, and conversely, rainfall duration is more so linked to stratiform precipitation. With this guiding framework, we have a set of science questions that we want to answer as a group. First being, what are the primary forcing mechanisms for extreme rainfall? Is it thermodynamics-based? Is it dynamics-based? Is it a combination of the two? Are we missing something and it's not thermodynamics or dynamics? Additionally, we can also ask if extreme rainfall is just the result of stronger forcing, or if there's something unique that's happening within extreme rainfall that sets it apart from regular run-of-the-mill rainfall. And then lastly, very broadly, how do we improve predictive skill for these extreme rainfall events? Now, a running thread between all of these different questions is that you still have to define extreme rainfall. It is contextual, but you still have to define it. And there's many ways that you can measure extreme rainfall. How do we pick apart what is the best way to measure extreme rainfall? So that leads into our seminar objective, which is discussing how do we best estimate extreme rainfall during PRECIP using the S-Pol radar. Are we able to capture high intensity rainfall as well as our high duration rainfall? And then, as I mentioned in my opening slide, Taiwan, where the PRECIP field campaign was held, is a very mountainous region. How do we optimize our rain rates from S-Pol to perform well within this complex terrain? And this is an even harder challenge when we recognize that S-Pol is in really close proximity to our two major mountain ranges within Taiwan, the Snow Mountain Range as well as the Central Mountain Range, which we'll touch on later on how that interacts with the radar and how it proves to become a challenge. While I will be giving some broader full campaign statistics for this sort of study, I find that it's better to contextualize these findings within a single event. The one that I'll be using is IOP1. It's the first major event of the campaign. It ran from May 26th to May 28th for a total of 48 hours. On the left, we are looking at a rain gauge corrected radar product from the Central Weather Administration from Taiwan for rainfall accumulations for the first IOP. And then we also show the rain gauges as well. Now, what's important to note is that these products, QP sums as well as the rain gauges, are hourly products, which really highlights why S-Pol is more suited for this sort of rainfall estimation study, because it has higher frequency than just 1 hour. There are many different ways in which we can study rainfall, especially within the context of radars. We're going to pick only a couple of these different methods. The first being the NCAR hybrid rain rate algorithm, which is based on Bringing It All 2009. It is reliant on particle identification, which you can see in the top row of this flowchart, where you have to look at either hail, heavy rain, snow, ice mixed, and then rain. What we find is that this hybrid approach actually performs significantly better than just using individual estimators on their own, such as reflectivity-based rain rates. Just looking at reflectivity-based rain rates can only tell you so much about what you're seeing within S-Pol domain. We also decided to choose NCAR hybrid because in past deployments of S-Pol, it seems to perform quite well. To contrast this, we're going to look at what is technically the newer rain rate algorithm. It's not quite that new, it's actually 10 years old. The specific attenuation-based rain rate. And we're doing this for two reasons in particular. The first being that, in theory, it's supposed to excel really well in both light and heavy rainfall. On the left is a figure from a review paper on specific attenuation-based rain rate, whereby we're looking at simulated rain rates compared to rain gauges in Oklahoma. And this is just fractional mean absolute error on the y-axis. And if we compare different estimators, such as RA, RZ, RZZDR, RKDP, RA is supposed to perform really well at pretty much all rain rates, except when you start dipping into higher rain rates, very high rain rates, I should say. The second reason as to why we're using specific attenuation-based rain rate is that it's been shown to perform quite well in complex terrain when compared to conventional rain rate estimates. On the left is a figure from Cox et al. 2019, where they're showing the improvements of their improvements to the NWS QPE output when you throw in RA. In the top row, we're showing the operational QPE on the left-hand side, where you can see some erroneous-looking data that is the result of complex terrain north of the radar. But when you swap over to RA, you actually see a mitigation of all of that clutter. That being said, we can also look at the bottom row where we do the same things. This radar is significantly more blocked by terrain. And while switching over to RA produces a better result, you can still notice that it is not exactly perfect. Being able to decipher as to how well RA can perform in complex terrain is still an ongoing topic within the field, and we're hoping that within our study we can help push along this discussion further. So briefly, I'll go over instrumentation, and this is the broad overview of instrumentation that was available during PRECIP, and no, EOL did not bring all of this instrumentation. A lot of this is actually operational from Taiwan. It's actually rather densely populated in terms of instrumentation, and that is especially when we compare it to Colorado. It's about a seventh the size of Colorado, so that much instrumentation on such a small island is really great in terms of studying rainfall. The primary instrument of this talk is S-Pol, which is located in the northwest coastline of Taiwan. Other instruments that I'm going to be talking about are the disdrometers, which are those blue little raindrop-shaped markers on the map, as well as the over 1,000 rain gauges available to us throughout this campaign. Briefly, S-Pol, it's a great radar. Some would argue it is the best radar. I kind of have to say that because I'm at EOL. We're using S-Pol because it simply is one of the best radars in the world. It has really high spatial resolution, and the scan rate is really fast when compared to other conventional radars. It's also quite sensitive to everything that we want it to be sensitive to: clouds, rain, hail, all of that with minimal attenuation, which is great. And the last point being, it was operational for pretty much the entire campaign, from May 25th to August 11th, which is really great. And throughout that entire 77-day period, we had a really ingenious scan strategy where our scan cycle is 12 minutes. Within that 12-minute cycle, we had 2 surveillance PPI scans, or the horizontal scan, as well as RHIs over cardinal directions, user-defined azimuths, as well as other instrumentation such as radars, MPDs, and disdrometers. For rain rate estimation, we really want both high vertical and horizontal coverage. So everything that I'm going to be talking about further on in this talk is just using SIR-1, which is one of our PPI scans that has the most elevation angles. And then briefly talking about those disdrometers, all of the disdrometers within the field were particle size velocity disdrometers, or parsivals. On the left is a picture of one of those via Google Maps that is being operated by the Central Weather Administration close to our radar. Very briefly, what the parsival disdrometer allows us to capture is hydrometeor size as well as fall velocity, and this tool is mainly used for precipitation microphysics. It's really great because it has 1-minute sampling intervals, which is pretty high. And it records data in 32 by 32 diameter and velocity bins. Really quickly, how it works is just there's a sheet of lasers, and when something falls through it, it can record how long that thing was passing through the laser as well as the diameter of it. But as with any instrumentation, it requires QC. I'm not going to go through all of the steps of this QC. I think it's important to note that this QC process is actually following what the Central Weather Administration does for their own QC. So while there's different ways in which you can QC parsable data, we find that it's best to follow what they're doing locally within Taiwan. A major point being they use a terminal velocity relationship. We're using Brandis et al. 2002, and then you take some percentage of that relationship. Here we're using 50% of that, and then within those green bins, that is all of our valid rainfall. Now I'll note, if you're trying to reproduce this, you might need to tweak it a little bit because we are excluding anything that is non-rain. So our focus is on rain, but if our parsival collects graupel or hail, we're actually throwing that out. So keep that in mind if you want to use this QC process. In terms of how that QC process performs, we can look on the left. We have a single disdrometer, and we're looking at full campaign statistics of rainfall accumulation on the x-axis from a co-located rain gauge, and then that's compared to the rain rate output from the disdrometer on the y-axis, and we're getting really good results, high correlation, low bias, all of that good stuff. That being said, not every disdrometer is going to look great, and this is mainly down to just how these disdrometers are calibrated. If they're miscalibrated, you can't QC beyond that. So we had to be selective on which disdrometers we used. We decided for this study we're just going to use the 4 closest disdrometers to S-Pol, which are those blue numbered disdrometers on the map on the right. And then we throw out everything else, so the red ones we're not going to actually use. The furthest disdrometer from S-Pol is about 75 kilometers, so that gives you a sense of the range between these. Now, what does this have to do with radars? Well, what you primarily can use disdrometer data for is for scattering simulations using T matrices. The T matrix scattering matrix sounds redundant. The T matrix was produced by Waterman in 1971. It essentially is simulating how electromagnetic scatter would happen on a non-spherical particle. It's really useful because you can simulate radar variables such as reflectivity or ZDR or KDP, et cetera, from just a disdrometer data set. And it gives you regional aspects of the microphysics that you might otherwise not know. In terms of how we're setting this up, it's quite simple. We have PyDSD and PyT matrix, which are quite useful for taking just QC'd disdrometer output and then feeding out radar variables that we want. In terms of our setup, we use a scattering frequency equivalent to that of S-Pol, scattering temperature of 20 degrees centigrade, which is quite normal for the subtropics, mean canting angle, or just how parallel that droplet is to the surface. 0 is quite normal. Canting standard deviation is 7.5 degrees, which is normal. And then drop aspect ratio model, we follow Thurian-Bringy 2005. Now that we've gone through all of that work, we can actually start to derive some rain rate coefficients. And these rain rate coefficients are actually optimized specifically for PRECIP because all of this disdrometer data was collected during PRECIP. So on the left, we're looking at reflectivity and rain rate derived solely through our disdrometer data, and we can fit curves to that to match new rain rate relationships that we want. We'll find that these PRECIP optimized coefficients are actually quite great when compared to the US convection coefficients, which are, I guess, the default within the LiDAR radar open software environment, which is how most of the S-Pol data was processed. And because we need a large sample size, we actually have to use the entire campaign's data set for this. But it's not going to do everything that we want it to do. Our disdrometers are not located everywhere. It doesn't have the exact coverage that S-Pol has, so you have to also add in bias correction to that. The bias correction essentially is just going to further optimize these rain rate relationships to work best for S-Pol. The method is quite simple. It's following Steiner et al. 1999. You take rainfall accumulation throughout the entire campaign from the radar and then from gauges, and then you just calculate bias from that. You can invert it and then multiply your rain rate coefficients by that, and you get a corrected bias, a corrected rain rate relationship. When we do that, we can have the most optimized form of our rain rate relationships. On the left is our RZ, or reflectivity-based rain rate. On the right is the KDP-based relationship. And we find that as we go from US convection, which is the white line, to disdrometer, the purple line, and the bias corrected, which is the red line, we're seeing shifts within our relationships such that lower reflectivities and KDPs are required to produce the same rain rates. So if we were to stay with our US convection-based coefficients, we would be under predicting rainfall, and we actually do see that. I'll also note that we did the same process for RZCDR, which is another component of the hybrid algorithm, and it performs relatively the same. So when we throw this in and we look at broad full campaign statistics, this is what it looks like for hybrid when we compare daily rainfall from gauges to radar using US coefficients. It looks okay. We have bias of about 78%, which is under predicting rainfall, as I previously mentioned. Still has high correlation, but as we transition into distrometer-based coefficients, we see slight improvements, and then when we bias correct that, we get the best product that we can. So this is really good in terms of bias. We're under predicting still, but only by about 5% or so. We still have high correlation. And while I don't show it here, it's important to note that hybrid outperforms all of the individual estimators on the run. So reflectivity-based rain rates are not going to perform as well as hybrid. We kind of already knew that, but it's good to validate that sort of intuition. If we wanted to perfectly correct this rainfall relationship to rid the bias, get it to 1-to-1 ratio, it would become more difficult. And that's just due to things that are slightly out of our control. If we overtune this, we might be over-predicting in low rain rate situations and then under-predicting in heavy rain rate situations. It's trickier to go beyond this point. But all that being said, we can compare how this performs to the QP sums and rain gauge data for IOP1. Starting at US convection, it is getting the locations correct. It is underperforming, as we said. We go up to distrometer, very slight noticeable improvements. And then as we go to bias corrected, it is probably the best that hybrid is going to get. Now, the locations are correct, but as previously mentioned, there is still some bias there. We are still under predicting rainfall. The rainfall maximum to the southwest of the radar is just barely cracking 300 millimeters, whereas in our rain gauge data set, we reached a maximum of 400 millimeters. So we're still under predicting quite a bit. And then some other regions of note where we're under predicting still is in northern Taiwan, where we see pretty much under predictions across the board. And that's something that's quite difficult to fix further. Now, the reason why we might think that we can't correct further, in my opinion, this is probably one of the major reasons, is partial beam blockage, which is due to complex terrain. On the right, we're looking at the cumulative beam extinction from the 0.5 degree elevation angle. So how much is your beam getting blocked essentially by terrain? And at the lowest elevation angle of our scan, we're quite blocked for most of the island, really. What this does is it can reduce reflectivity along the way. And if there's too much blockage, then you'll have to go up to higher elevation angles to get rain rate estimations, which on its own is not a bad thing to do. But what I've also been finding is that within the PRECIP field campaign, rain rates tend to be the highest the closer we are to the surface. So if we have to go up to higher elevation angles, we are still going to underpredict rainfall just because we're just not seeing the rainfall that's being seen at the surface, essentially. Now, this is a pretty good segue into why RA, or specific attenuation-based rain rate, is meant to tackle these problems and perform better. The reason why RA is meant to do really well within complex terrain can be boiled down within the equation itself. In theory, you have reflectivity on both the numerator and denominator of your attenuation equation. Thereby, if you have decreases in reflectivity due to some beam blockage, the decrease is on the numerator and the denominator, so you're just getting a localized decrease in reflectivity based on the actual rainfall, not the blockage signatures that we're seeing. And in practice, it also works quite well, especially within what NWS uses. On the bottom is a result from Rishkov-Fidel 2014 from Vance, Oklahoma. On the left is reflectivity, and to the southwest of the radar, there's very clear evidence of some beam blockage signatures, very erroneous looking data that's going along the radial. And that gets transferred over into the reflectivity based rain rate. But if you swap over to RA, it seems like a lot of that erroneous looking beam blockage signature in the rain rates gets mitigated. So that gives us some confidence that RA should perform really well. Now, I say that, but when we try to implement it, it doesn't look as good as we want it to be. First, some positives. The rainfall maximum to the southwest of the radar does look significantly better compared to the hybrid algorithm. But to the southeast of the radar, you have very erroneous looking data, mostly due to blockage and clutter. And then to the northeast, where we have beam blockage, we still have under predictions of rainfall, similar to how our hybrid was performing. So if I was to say, is this a good or bad rain rate algorithm, I would probably say bad. It's not, it has its strengths, but it's also not as great as we want it to be. And I think trying to understand why it's not performing well, we kind of have to dig into the equations itself. Starting with what exactly is attenuation. Attenuation is just the loss of power due to absorption through hydrometeors within the atmosphere. The main components within this method of finding attenuation, or specific attenuation, I should say, is the A equation, as I showed prior, as well as PIA, or path integrated attenuation. A key component of that is finding the difference of phi dp at two different radials, phi dp being how much your EM wave is getting polarized. And in other studies, we've also found that this difference in phi dp is directly related to how much attenuation you see along array. Thus, that's how we have path integrated attenuation. So realistically, to get specific attenuation, all you really need is reflectivity and phi dp, which is why this method is called Z-phi. But in practice, you actually need quite a bit more, and there's a lot more assumptions that you have to kind of work into it. And there's still problems that occur within it. And I'll go through some of those problems real briefly. The first being intrusion of wet ice along your array. Let's say we have some theoretical data, some fake data of reflectivity and phi dp along array. When we introduce wet ice into the equation between those dashed lines, we actually see some uptick within our reflectivity, that if an equivalent volume you only had liquid rain, your reflectivity would actually be quite lower. And that's going to affect our attenuation calculations. A specific attenuation just doesn't work well in wet ice. It's a known problem. Trying to mitigate that is still a topic of debate within the specific attenuation community. There are ways of getting around this. You could just add some segmentation to your array, change R1 and R2 to be before and after your wet ice. And then within the wet ice region, you can just use RKDP, just because phi dp is a little bit more resilient to the intrusion of wet ice. Now, trying to find those bounds with which wet ice is occurring is very difficult, and it's still a major problem with RA. Another problem being clutter. Clutter introduces noise within our variables. We find noise in phi dp, we find noise in reflectivity. If we're trying to find R1 and R2, which is required for specific attenuation, if you introduce some noise, you get some bogus phi dp at R1. This could also happen at any point along the array. And while the errors may only seem obvious within this region of clutter, it actually propagates along the entire array, just because of this I term within the specific attenuation equation is actually integrating reflectivity along the array. So if you're integrating still your clutter, or if you're integrating clutter along the array, it's going to spit out a erroneous looking attenuation. Similar to wet ice, you can try and just shift that over those starting points along your array. It's still quite difficult to do that. If you nip just a little bit of the clutter, it can still throw off your specific attenuation measurements. And if you throw out too much data, then how valid is your specific attenuation measurements? The last problem that I'll kind of touch on, there's still some other problems, but last problem is partial beam blockage. And yes, I did say that RA is meant to do really well within partial beam blockage regions, but I think there are cases where it still doesn't perform well. What I've been finding within the S-Pol data set is that if we see some step function jump of terrain along array, here it's noted by the brown line, I typically spot some noise within the phi-dp field, which on its own, it's not a big problem because we're only using the starting and end points of our phi-dp. But, and this happens quite often, if our partial beam blockage jump is right up close to the starting or end gates for phi-dp, that's where we do see problems. And it's hard to really separate these out. I could try and move our ending R2 to be for that partial beam blockage, but that's still very difficult. And this problem doesn't always occur. The operational radars that they use in Taiwan actually have a version of RA that segments the ray to mitigate this problem, but they had to use a long climatology of rainfall data to mitigate these partial beam blockage problems. And we just don't have that luxury with 3 months of data, unfortunately. So we have to think of ways of kind of mitigating that. But with all that being said, we can return to what is the first version of RA. Again, it doesn't do very well, even if we're trying to faithfully implement the Z-phi equations for specific attenuation. Now, I can jump ahead a few versions to version 3, and I can say it probably performs a lot better. We see improvements to the rainfall maxima to the southwest of the radar. A lot of the noise that was to the southeast that had to do with the mountains is cleared up quite a bit, though this is still not a perfect and ideal product that we would want. We still underpredict rainfall in northern Taiwan. And this feature to the southeast is still not, it doesn't look correct. And you can't see the exact values, but this is seeing rainfall amounts upwards of 500 millimeters in 48 hours, which is just incorrect when the rainfall maximum in rain gauges is over here, and it's 400 millimeters. So there's still something going on there that we can't quite pinpoint. But that made us think that if we have ongoing problems within RA, perhaps there's some issues with how we're selecting our elevation angles. For rainfall estimation, you have to pick an elevation angle that is as low to the surface as we can get. As I said previously, we're finding that rainfall is highest and closest to the truth the closer we are to the surface. But if we have poor data quality, for example, if we have low signal to noise ratio, or you have some amount of partial beam blockage, you have to go up a higher elevation angle. And that's what we see on the left figure. This is the selected elevation angle for a given time. And we find for much of Taiwan, you actually have to go up to at least 1 degree to get valid data. It's just too much blockage there. But on the other side, over the ocean, you can use that 0.5 degree tilt, which is really great. Now, I believe that one of the reasons why RA is not performing well is because just there's too much noise that is not getting filtered out through this selection process. So to mitigate that, I've updated the selection process. We're keeping the same SNR thresholding. That's to throw out any noise within our data set. But additionally, I've also added a rho-HV threshold. So if there's too much clutter along a ray, then you'll also have to go up to a higher elevation angle. We also threw out the partial beam blockage threshold just because RA is supposed to do really good in high beam blockage areas, so why keep it? Additionally, I think the rho-HV threshold is still not going to do exactly everything that we want it to do. So between the azimuths of 20 and 195 degrees, we just start elevation angles at 2 degrees. We're trying to see over the clutter as much as possible. This might potentially lead to underpredictions further away from the radar just because you have to look so much higher up. Close to the radar, probably not going to get as much of an issue just because the angles are low relative to how far away you are. So in practice, this brings us to 3.5 or whatever. And this is probably the best result we can get. We actually get a fully intact rainfall maxima to the southwest of the radar, which is everything that we wanted it to be. We still get some noise to the southeast of the radar that doesn't look correct, and those erroneous high rainfall values within that region are still there. You still get rainfall amounts of about 450 millimeters when in the rain gauge data you're getting closer to 200 millimeters, so still not looking great. Additionally, we still have underpredictions in northern Taiwan, which may lead to something larger than just trying to filter and threshold for certain changes. It might be an issue of we're just looking too high up no matter what elevation angle we're looking at. We might have to use some vertical profile of rain techniques or VPR to scale those rain rates to be higher than they're normally supposed to be. But for all of those problems, I still think that this is a relatively good product, especially in comparison to the hybrid algorithm, which was under-predicting those high rainfall amounts to the southwest of the radar. And it still has problems with beam blockage. So RA is working really well, but this brings RA into a bigger discussion on when is RA actually valid. A lot of the literature says that RA is actually, in theory, it's supposed to do well at all rain rates, but in practice, you might need high amounts of phase shift for your path integrated attenuation to be valid. How do we fit this into some algorithm to perform RA when it's most optimal? And how I'm approaching this is through a new rain rate algorithm. I'll just call it rsynth for synthetic rain rate algorithm. A lot of this is taking from the NCAR hybrid algorithm, but it also takes some components from what the Central Weather Administration uses as well. One of the things that we wanted to cut back on from the hybrid algorithm is the reliance on PID. While PID works great in most scenarios, you can't confirm that it's always going to work as well as we want it to do. So for determining when we use a snowfall or mixed phase rain rate, we just use a temperature dependence, which is taken from some radiosonde or from model data. The first thing that is actually quite odd is that we choose a lower bound for elevation angles of 2 degrees. The reason being is that NWS as well as the Central Weather Administration don't actually use RA above about 1 degree or so. And that's because if you tilt your angle up higher and higher, more of your ray is going to be above the melting layer, and that introduces wet ice. And as I've said previously, wet ice is going to introduce problems with your RA. So we chose 2 degrees mostly because SIR2, the other scan, has a maximum elevation angle of 2 degrees. So we want we want maximum benefit to both SIR1 and SIR2. The second change to the algorithm that is actually quite unique is that phi dp difference threshold. So we need to see a phase shift of 5 degrees or greater to decide if we want to go to RA. In literature, Rishkoff et al. 2014 typically says maybe 3 degrees is the correct amount. The Central Weather Administration uses 5 degrees. It's still not actually certain what is the valid amount of phase shift required for RA to work. The last criteria to get to RA is just a high reflectivity check. If your reflectivity is greater than 50 dBz, you might expect some hail within your volume. Therefore, wet ice, it's not good. Shouldn't use RA in that situation. If all those things go well, then you can use RA, and that is its most optimal state. Otherwise, we default back to the rain portion of the NCAR hybrid algorithm, so something that has been tested and known to do relatively well. So when we implement all of this, we get a really good result. It's somewhat similar to how RA looks, but we do see some reduction of rainfall to the southeast of the radar that was not correct in the previous version of RA. And then we also see increases in rainfall in northern Taiwan. Not as much as the rain gauges and QP sums, but it is still somewhat better than just RA on its own. We're still tweaking the synthetic rain rate algorithm to hopefully get it to perform even better. But we find that this is working really well for what it's worth. So I'll summarize this portion just that to be able to study extreme rainfall, we actually have to be able to measure extreme rainfall. We find that the attenuation-based rain rate, or RA, improves S-Pol rain rate estimation in comparison to the NCAR hybrid algorithm. And this is most noticeable within the most intense rainfall of ILP1. And then when we combine RA with the NCAR hybrid algorithm, it gives us our best rain rate estimation for Taiwan's mountainous terrain. Now to look further ahead, now that we have these extreme rainfall measurements, how do we determine what's causing it? And this goes back to the initial concept of PRECIP, thinking about rainfall intensity and duration. Myself, I'm most interested in what the microphysics are doing to influence extreme rainfall in this event as well as other events within PRECIP. In addition, I also am interested in the terrain influence on the meso to microscale interactions in heavy rainfall formation. And how I'm starting to look at this is in a 1D aspect. So now that we have now that we have reliable rain rate estimates, I can pinpoint where the highest rainfall is, which is that gray dot on the left-hand side. With that gray dot, we'll take a 1D column of data, and I can use a microphysical fingerprinting technique produced by Kumjin et al. And further explained in Kumjin et al. 2022. Fingerprinting is a way of trying to capture microphysical processes, in this case warm rain processes, within a column using radar data. So you just difference reflectivity and ZDR at 2 different levels, and you can somewhat gather what's happening within the column. When we do this for May 26th, the first day of ILP1, we find that there's some signatures of coalescence as well as breakup within the column. And if you have somewhat of a keen eye, you can also note that the coalescence as well as the breakup are somewhat diurnally linked, as all of these scatter points are actually colored by the day, time of day, I should say. So to further try and decipher what's causing this split within breakup and coalescence, and really, is it tied to intensity and duration, which is the main objective of PRECIP, we can turn to using the echo classification tool, which Ricky gave a seminar on back in May. So we take the same day, we look in the same column, and we plot up the convective stratiform classification using echo. Coalescence we found was earlier on in the day, and that corresponds to predominantly convection, mid-level convection within the column. Conversely, the signatures of breakup, which were later in the day, closer to nightfall, are marred by mixed phase precipitation as well as stratiform precipitation. So really taking surface measurements of rainfall, expanding this to the microphysics at play to force that, and then starting to think about the broader mesoscale phenomenon. Forcing those microphysics is really where I plan on going with this further down the road. But this is all just preliminary work. So with that, I'm going to stop there and I'll take some questions.
Thank you, Ian. That was a really beautiful, beautiful presentation. We have time for questions virtually and in person. Does anyone have any questions for Ian? What do you plan to do? We have a question. How do I get this? Can you please pass that down to her? Thanks.
Thanks for the presentation. I'm wondering how sensitive your analysis is on the specific wavelength of S-Pol. As you shift 50 megahertz one way or the other, how sensitive are your assumptions about the microphysics? That's one of them. And then the other is your disdrometer measurements are all at surface level, and basically none of the radar data measurements are from surface level. So does that give you information of the dynamics going on between those two elevations, or just highlight the lack of being able to fill in that gap?
Sure. So starting with the sensitivity of wavelength, I don't know how sensitive the wavelength is for specific attenuation. From what I've seen in the literature, they don't typically modulate that frequency by small amounts, but if you compare it from S-band to C-band, it's actually quite different, the results you get. And you get larger spread as you go from S-band to C-band in terms of the quality of data. So that's my assumption for RA, that it's probably not going to be super sensitive to a small change in your wavelength. In terms of your hybrid algorithm, how sensitive that is to wavelength, it would boil down to how sensitive reflectivity, ZDR, and KDP are, especially within your volume. And I just haven't looked at that enough to really know what's going on. It would be rather poignant to look at that, just because the other radars on the island are S-band, but they're 10 centimeters, whereas S-Pol is at about 10.5. So it would probably modulate things quite a bit.
And for this deployment, we shifted the wavelength a little bit given the military's hold on that frequency.
Yeah. I would have to check and see if there's a shift in performance when we made that change, and I don't remember the date off the top of my head, so I can look at that further. Yeah, okay. So then I'll look into that, but I don't think it'll make a large difference for both of those estimators. The second question was with regards to disdrometers at the surface and then the rainfall that we're collecting. I think that feeds into why we have to do bias correction, because we are still under-predicting rainfall. It's hard to make assumptions of what the rainfall is actually looking like within the atmosphere just based on the disdrometer data we see even if we are at the lowest elevation angle, you aren't actually capturing what's at the surface and vice versa. So yes, there is an error of assumptions that is required to get rain rate estimates from disdrometer data. But I believe bias correction should mitigate a lot of that for the most part. Yeah.
For the errors that you saw, did you dichotomize that, if that's a word, into stratiform rain versus convective rain? Was one or the other producing more of the error?
From what I saw, it's actually, I'm assuming we're talking about the specific attenuation, or just in general.
You said that in general that you're having errors, underestimating the amount of rain that was coming down. And so is that a problem on just particular days? Is it a problem in stratiform? Is it a problem in convective? Is it a problem everywhere? Is there?
Yeah, I believe it's predominantly stratiform rainfall. When we get lower rain rates in specific attenuation in particular, we're not going to get as much of a phase shift. So trying to tease out how much attenuation we're getting is going to be really difficult. Now, if we have really high rain rates, specific attenuation is going to light up and it should perform really well. It's not going to be as erroneous trying to look higher up in this atmosphere versus lower, just because in higher rain rates, we're not seeing as much of a difference in the rainfall and elevation when compared to stratiform rainfall. There's some interesting microphysics that we still have to think about in why that performs the way it does. But we believe mostly the stratiform rainfall is a challenge still.
Is there any possibility that the raindrops are growing as they're coming down, and so you actually do get more rainfall at the surface than there is evidence up at, higher up, wherever, a kilometer up, or two kilometers up, or wherever you're making your measurements?
Yeah, I'd have to think of a way of isolating that. I mean, the fingerprinting technique itself should kind of point to that. You take the difference of reflectivity at two different levels, you can see if the drops are actually growing. It's a little difficult to display that over entire volume. I'm still trying to think of ways of how to do that. But even within one case, in this example here, we see breakup and coalescence at the same location, and they're separated by a couple hours. So it's really hard to blanket say coalescence is happening in general for this event. It's not as black and white typically.
I had another question, but I forgot because of my age.
Thanks, Ian. Nice talk. You've got a lot of detail earlier, but this is the most interesting part of the talk, which you sort of glossed over pretty fast. So the fingerprinting analysis, how confident are people that it's valid? Because you're saying, we've got coalescence. It's like, okay, is that real?
I think it depends on how much averaging you're doing, essentially. I've seen fingerprinting where you're just taking averages at 100-meter bin altitudes, and it's not a robust enough method to kind of determine how much change in reflectivity and ZDR we're finding. When I did it, I chose 500-meter elevations and difference those. It's a little bit more robust, but trying to quantify how well it performs is quite difficult. I think when we throw in the echo classification tool, you can actually put some rhyme or reason as to why we see the fingerprinting that we do. So on its own, it's a little difficult to tell how well it's performing, but when we pair it with other tools, I think that's when it becomes a little bit more powerful, a little bit more understandable, really.
Yeah, good, thanks.
So the RKDP equation that you used, that's a tropical RKDP, tuned for tropical rainfall. It comes back to mind here. Back in like 1996, we had a real heavy downpour over a series of days up in Fort Collins, and our typical rain rate estimators, couldn't predict it. We were like coming, 50% less than what was actually measured with rain gauges up there. So they finally decided that it was a tropical rainfall event, and they simply had to tweak their coefficients on the RKTB relationship to get the rain gauge estimates and the RKDP estimates to agree.
Yeah.
Was there a question in there?
Yeah.
In other words,
yeah.
I was just curious that the RKDP relationship that you were using was a tropical one that would give you the right amount of rainfall.
Yeah, I believe the original RKDP relationship, which is from U.S. convection, I believe that was derived in Florida. So yeah, it is a tropical origin, though the rainfall that they spotted in Florida just didn't correspond to the rainfall we're getting in Taiwan. So it's still tropical, but you have to make it more extreme, I guess.
So your bias correction depended upon distrometer observations. In the absence of a distrometer, would you be able to get that information from, say, satellites or climatology or?
You could do from climatology, and in fact, you would probably just be copying what the Central Weather Administration does. But I think going back to one of the first questions we had, the climatology from Taiwan is using their operational radars, and their wavelengths are slightly different from what we have for S-Pol. So I don't know if that would perform as well as we want it to do. And then in terms of satellite observations, we've discussed this topic with other colleagues trying to do satellite observations of rainfall within Taiwan. And I don't think they're able to capture the high enough rain rates that we're seeing within Taiwan. They can get general location and some scale of light to medium to high rainfall, but they can't really determine the actual high amounts. So it might be scaled back some degree. I don't know if you'd be able to bias correct that the same. It'd be difficult to say.
They'd still underestimate.
Yeah,
They'd still
I
underestimate
think
the
so,
rainfall,
yeah.
so you're really not doing a correction.
Yeah.
Just maybe adjusting it a little bit.
Possibly, yeah.
Well, we're almost at our seminar hour. Since we don't have any further questions and we have no questions online, let's please thank our speaker.